Now that we've learned about arithmetic sequences in which the pattern is built by adding the same value each time, today we're going to look at geometric sequences in which terms are built by multiplication. So it's not just adding 5, adding 5, adding 5, it's multiplying by 5, multiplying by 5, multiplying by 5. We call that the common ratio, which you'll see referred to in the formulas as R. So D represents difference, and that's what we are adding. R represents ratio, and that's what we'll be multiplying by. You're going to see a lot of similar ideas between geometric sequences and arithmetic sequences. We just have to adjust the formulas to show the change of operation. All right, so the general form of a geometric sequence, and this would be our explicit formula, so we can find any term in the sequence by using this, would be AN equals A1, so first term, times R, there's our common ratio, to the n minus 1 power. This should actually remind you of an exponential function, where we have a beginning term, we're multiplying by something so many times. So again, while arithmetic sequences are linear, geometric sequences are more exponential. There isn't an alternate form for, oh my goodness, I'm having trouble talking. There isn't an alternate form for this, so just that one formula that we will be using. Um, well, let's go ahead and make one up. I don't know if I have one on the next page. I do. Okay, never mind. We'll keep going. So I would like to find an expression for each of these, and then we're going to find that indicated term. So I've given you the sequence 2, 8, 32, 128, etc. I would like to find A12. So again, if this is geometric, then we know we can use the formula A1, so first term times R to the n minus 1 to write our expression. So we need to know, well, first let's identify and make sure this is geometric. So when we go from one term to the next, is there a common value that we are multiplying by? And hopefully you should be like, yeah, we're multiplying by 4. 2 times 4 is 8, 8 times 4 is 32, 32 times 4 is 128, etc. So this 4 is our R value. And that's really all that we need to know here, aside from what the first term is. So A1 is our first term is 2. R was 4 because that's what we're multiplying by. And n minus 1 just indicates the term minus 1. So that is our expression. There's no extra work to be done, nothing else to identify that's not already there. So geometric are pretty explicit that way. Haha. Okay, so now I'd like to go ahead and find A12. So A12 just means I'm plugging 12 in. So that would be 2 times 4 to the 12 minus 1, or 2 times 4 to the 11th. And again, I'm going to let you calculate that. I don't have a calculator on me, but you'll see, just like with exponential functions, these guys get big really fast, especially in cases in which we're multiplying by 4 11 times. So don't be surprised when you get some big numbers. Or, like if we look at letter B, maybe some small numbers. So let's check out letter B. We are given the expression 6, 3, 3 halves, 3 fourths, dot, 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 and we're asked to find A8. So again, I want to start by identifying R. Let's just make sure that this actually is geometric. So when we go from 6 to 3, or 3 to 3 halves, or 3 halves to 3 fourths, it looks like we're dividing by 2. Now, dividing by 2 is not something that we can put into a geometric sequence. We've got to write this in terms of multiplication. So if we're dividing by 2, then we're going to have to say that R is 1 half. All right, so we will have some fractions here, which is fine because we like fractions. So if I go to my sequence, AN equals A1, which is 6, multiplying by my R value, which is a half, I'm going to throw in parentheses, to the exponent n minus 1. So that would be the expression for the sequence. There's my explicit formula. So now I can plug in any number and find that value. And in this case, let's go ahead and find the 8th term. So A8 would be 6 times 1 half to the 8 minus 1, or 6 times 1 half to the 7th. And again, I don't know what that is. I would be finding 2 to the 7th and multiplying 6 times 1 over that. And that will give us that value. Now, I would say on this one, because all of our terms in the sequence are fractions, let's leave our answer as a fraction, please. So again, find 2 to the 7th, do 6 times the 1 over that. So it'll end up just being 6 over whatever 2 to the 7th is. All right. Now, do you remember with arithmetic sequences, we had a problem in which I gave you two different terms, and then I asked you to find, I think, just the first three, and then we came up with an expression for it. This one is similar. I'm giving you two terms in a geometric sequence, and I really should specify that this is geometric. So shame on me for not saying that. Geometric. There we go. Um, but this time I just want to find a 14th term. I want to kind of build on what I know to find the 14th term. So we identified with our arithmetic sequence what the d value was, what the addition was, the slope. I want to kind of find that with these two terms also. But of course, instead of finding d, we'll be finding r, which is our ratio. So here's what I know. I know the fourth term is 125. I know the 10th term is 125 over 64. So if I'm going from term 4 to term 10, then I am multiplying by r. Oops, silly dots. I am multiplying by r 6 times, right? Because that's how many terms away they are from each other, and r is always a multiplication. So I'm multiplying by r 6 times. So now let's put this in terms of the numbers I have. To go from A4 to A10, so 125 to 125 over 64, I need to multiply by r 6 times. So A4 times r to the 6th equals A10. So that's what I know. Okay, so again, here's my A4. If I multiply by r 6 times, I'm going to get to A10. All right, so let's see if we can solve for r. I'm going to start this problem by dividing that 125 out. Now, if I have the fraction 125 over 64, and I'm dividing by 125, I'm going to come up here. That tells me it's 125 over 64 divided by 125, right? Dividing by a number is the same as multiplying by its reciprocal. So 125 over 64 times 1 over 125. So you can see that these 125s are just canceling. So it looks like r to the 6th is 1 over 64. All right. So again, I'm just dividing both sides by 125. It just got a little messy because of the fractions, but I'm at the point where r to the 6th is 1/64th. And if r to the 6th is 1/64th, I can take a 6th root, not a square root, but a 6th root, to get r by itself. And I'm pretty sure the 6th root of 64 is just 2. So r is a half. How about that? So this sequence is being built by multiplying by halves. Okay, just again, got a little messy because of the fractions. Okay, so where were we? We are trying to find A14. We have some options. We could write up a formula for this thing, except that we don't know what the first term was. So that is kind of out. Or we could build on what we do know. If I know the fourth term is 125 and I'm trying to find the 14th term, I just need to multiply by r 10 times because those are 10 terms away from each other. Or I could build from the 10th term. If I'm going to go from the 10th term to the 14th term, so that to that, I can multiply by r 4 times. And I would rather do that, especially as we're working with a fraction. So I'm going to scooch just over a little bit because that's all we need. So I know A14 would be A10 times r 4 times. Right? If you need to write it out with blanks and so you can see that, then by all means go for it. But I just know these are 4 terms away from each other, which means I've multiplied by r 4 times. A10 was 125 over 64. R is a half, so times 1/2 to the 4th. So that's what we're multiplying out. So it's going to be 125 times 1, because that's 1 to the 4th. And then I don't know well, let's see, 2 to the 4th I think is 16. So whatever 64 times 16 will be our denominator. Okay, so it really is similar to the arithmetic one. I had to kind of go back and figure out what is my building block? What is that I'm multiplying by? So I did that. I found r was a half, and then I used that value to build on what I already had. So I ended up with a sub 14 is 125 over 64 times 16. Okay, so that sums everything up with geometric sequences. So our explicit formula, which is that a1 times r to the n minus 1, and then how we can use it. Now let's talk sums. A geometric sequence or series, when we go to sums, really, actually has two options for sums. We can find, I know it's crazy, and we'll talk about it. We can find the sum of a finite sequence. Well, that makes sense because if I have 10 terms, I can add them up, right? But there are actually some sequences that are infinite that we can find sums of. So we'll look at some examples. Not every geometric sequence can find a sum if it's infinite, but there are definitely some that you can. Okay, so we'll talk about the difference and how it actually works. So let's start with the finite. So the sum of our finite sequence. So it's going to look like the arithmetic one. We're going to say S sub n. So sum of n terms is a1, so first term, times the quantity 1 minus r to the n over 1 minus r. Okay, so a1 times 1 minus r to the n over 1 minus r. So notice what the information is that we need. We need to know first term. We need to know r. We'll put that in a couple places. And we need to know how many terms there are. Also notice the numerator. Take a look at it for me. It's just r being raised to the n. It's not the whole 1 minus r being raised to the n. Okay, so 1 minus r to the n is what we'll be doing. Okay, so let's go ahead and find the sum. Now, this first sequence is written in summation notation for us, or in sigma notation. So let's see if we can pick out our pieces. So I need to know what A1 is. And A1 can be found by plugging in whatever that bottom is to the variable. So A1 would be 4 times 0.3 to the first, which would be 4 times 0.3, so 1.2. Okay, so there's my A1. I also need to know what R is. R, and I'm going to show you here where it is in a sec, but R we can always find by identifying the next term and seeing what the multiplier is. So let's go ahead and find A2. So A2 would be, I guess I'll go up here. A2 would be 4 times 0.3 squared, which is 4 times 0.09, and that is 0.36. Okay, so if A1 is 1.2 and A2 is 0.36, we have multiplied by 0.3. So here's the nice thing about sigma notation. Do you see the 0.3 in the formula or in the sigma? You should. It's right there. Whatever is being raised to the power, that is your R. So there's a nice little shortcut. Now, is the first term your A1? No, it wasn't. We had to find A1 by actually plugging in that bottom. So don't assume that the first thing is your A1 just because the second thing is the R. Not always going to work that way. Sometimes it will, but not always. Okay, so anyway, we need to know three things. We need to know A1, we needed to know R, and we also need to know N. How many terms are there? So I can look at that in my sigma also. If we are going to be plugging in the numbers from 1 to 12, then n equals 12. Okay? But again, I don't want you to assume things. Just because the top is 12 does not mean that there are 12 terms. Because if the bottom was something else, that would adjust the number of terms. So here's what I want you to think about. The n is the top value minus the bottom, but then we have to add 1. Okay, so if we had gone from like 3 to 12, it'd be 12 minus 3 plus 1. All right, so again, for our case, n is 12, but don't assume. So we're ready for the sum. So the sum of our 12 terms will be A1, so we said 1.2 times 1 minus 0.3 to the 12th over 1 minus 0.3. And that will be the sum. Again, I will let you plug that in the calculator. We'll check that value tomorrow. So there's our finite. We've got a nice little formula for it. But again, there is an option for finding the sum of infinite geometric sequences. Now, like I said, not every geometric sequence will be able to find a sum. Okay, if I gave you the sequence 2, 4, 8, 16, 32, etc., in which we're building by multiplying by 2, there is no sum for that. That is going to be infinite. These numbers are going to be huge. It's like an exponential function, right? But what if I did the opposite? What if I gave you the sequence 32, 16, 8, 4, 2, 1, dot, dot, dot? That one we can actually find the sum for, because as these numbers are just getting multiplied by a half, eventually they're going to get so teeny, 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 tiny that they won't affect the actual sum. Okay? So if the absolute value of, not n, shoot, if the absolute value of your r, so what you're multiplying by, is less than 1, then we can find a sum. So that's basically telling me as long as my consecutive numbers are getting smaller, they're getting closer to 0, then we can find a sum. But that's only the only kinds of infinite sums we can find. So if that is true, then we can say the sum is a1 over 1 minus r. It gets much simpler when we don't have to worry about what n is. Okay, but again, if r is less than 1, an absolute value is just saying it doesn't matter if it's positive or negative. As long as that number is less than 1, we can find a sum. So let's go ahead and do this last one. I'd like to find the sum. I can tell that it's infinite because there's an infinity sign here. So I need to check to see if I can find a sum. I want to check my r value. Remember, we said r is the number that's being raised to the power. So r is the 1/5. Is that number less than 1? It sure is. So that means we can go ahead and find our sum. Okay, if that was 6/5, or if it was something more than 1, then I would stop here and I would say there is no sum. So that's something that you don't actually have to do. Okay. All right, so r is 1/5. That means I can find my sum. Oh, but I need to know what a1 is. So a1 is what I'm going to get by plugging in the number 1. So 4 times 1/5 to the first. Looks like it's just 4/5. Oops. So now my sum is 4/5 over 1 minus 1/5. So that's 4/5 over 4/5. Well, that's interesting. So if we were to write out a whole bunch of terms in this infinite series, and then we were to add them together, we would end up with a value of 1. Crazy, huh? Okay, so again, quick recap. 2 sum formulas. One applies to infinite ones. One applies to finite. Here it is. Make sure you got those. And then we've got our geometric sequence formula that is just building on a1, r, and n minus 1.